Okay. So in project 3, we are going to be talking about a switch debouncer. So we'll start talking about why do we need a debouncer circuit? Can we get a hardware switch debouncer? What's the need? How are we doing it? Using a 555 timer. Um, and we'll at the end goal of project 3 is to use a debounced switch to trigger a counter. So a counter, we are going to use the same counter that we used in experiment 7, the 4-bit counter, which was the uh, 74393 chip. So this was the 4-bit counter, and as the clock input of that counter, we are going to use a debounced switch to trigger the 4-bit counter. So let's talk about why we need a switch debouncer in the first place. Note that a lot of the switch debouncers can be implemented in hardware, but you could also have a situation where you implement the debouncing in software. So they're both types. Over here, we are focusing on the hardware debouncer. So why do we need it? So for example, if I look at a figure, this is voltage from the analog discovery. The blue line over here indicates that if I have a switch that changes state from low to high, and after some time it comes back to low, it is not a very clean transition from low to high, and there is a lot of noise even in the middle here. And while it comes down, it's not a clean change of state. There is a bounce involved in the switch. That's because of the mechanical properties of a switch not being able to cleanly go from low to high and high to low. So there is going to be a bounce in switches. And there are lots of resources that are linked in project 3 on the class website. And I would really highly recommend you to go through that to get a sense of, what are the different types of switches that you might see, and what are the typical bounce times, right? So how much time does it bounce? Does it bounce forever, or does it bounce for a few milliseconds, a few tens of milliseconds? So I would, and how does it relate to the type of the switch? So we have several types of switches in project 3. The one that I'm going to use in the hardware is going to be a push button, and there could be other types of switches that have this issue of bounce. So the problem is not being able to cleanly go from one state to the other, and this could lead to a big problem. For example, if we were to trigger the same 4-bit counter using a bouncy switch, what could happen is, instead of going from, say, if I'm responding to the negative edge of the switch, if I'm responding to the negative edge of the switch, I've got several negative edges of the switch because it was bouncing. So it will accidentally go and count all those as pulses. So we don't want that to happen. We want that to only respond to that negative edge because that was intended. All the others were the bounce, and they were not intended. So in project 3, our input is going to be this sort of a blue line, which is the property of a bouncy switch, and our output is going to be debounced output, which is indicated by that red dashed line over there. So we want our switch to go from low to high state cleanly and then come back to low state very cleanly. So that's the objective of this bouncy switch. So we have talked about the goal. Um, the notes over here talk about the fact that we can do this in software, which we have talked about. So let's move on. So we are trying to do this, right? Let's see. So typically, if you are doing this in class, you would go online and look for uh, example debouncer circuits that are based on the 555 timer, and you would pick out a design that appeals to you. now that I'm building the circuits for you, just to be consistent, please note that I have taken an image of the 555 timer based debouncer, switch debouncer, that looks like this. So all I did was go to Google and search for switch debouncer 555, and the first image that came up is this. So I've taken up this as my circuit that I'm going to build. So it's based off of 555 timer, and the all the details of the 555 timer were discussed in the previous lecture. And in experiment 7, it was operating in the uh, astable mode. Experiment 7, we had the 555 timer operate in the astable mode, which means that it is going to be a free running square wave. It's going to keep going back and forth between low and high, depending on the charging and discharging of a capacitor. However, in project 3, we are going to operate the same 555 timer in a monostable mode, because we don't want that switch to keep going high low. We just want the output to be one clean pulse, suggested by the output pin number 3 there. Low to high, no bounce, come back low after some time, after the typical bounce times of the switch, right? So you don't want to come back down too early, and you don't want to come down too late, because if you come down too early, then you are essentially not doing the debouncing, and if you come down too late, then you have spent time in the high state for too long. So that's not ideal. You want to be able to use the switch to do the other pulse quickly. You don't want to spend high time too long. So that's going to be your output. But as you notice, this is not going on forever. This is just one clean pulse and done. And you have a switch that controls, that is getting debounced. Where is that switch? The switch is connected to pin number 2 there, indicated as S1. So that's a bouncy switch. And the output over here on pin 3 indicates the same switching behavior of S1, however, it is the debounced output. So that's the goal. And we are using 555 timer over here. And as you can see, a few key differences between the astable mode for experiment 7 and monostable mode for project 3. We are not actually using R1, R2 as we were. Pin 2 and 6 are not connected to the same point. Over here, you have a slightly different configuration. So let us start talking about R1 and C1. You still have C1 getting charged through R1, but that happens, or that is in response to a switch. So when the switch closes, pin number 2, so when switch closes, S1 closes, you have pin number 2 reading 0 volts, ground. So as you can see, if the switch closes, pin number 2 is connected to ground here. And pin number 2 is in our design internal to the 555 timer. Pin number 2 is essentially the input to the trigger comparator. There were two comparators. Pin 2 is the input to the trigger comparator, the one at the bottom. Let's see, how about when it is open? When switch 1 is open, it means that pin 2, as we have so as you can see, if this is, oh sorry, this should be, I switched it. If this closes, that is 0 volts. Yes, if this is open, then that means there is no connection there. Now pin 2 is going to be connected to high, so it is pulled up to a high voltage, say 5 volts, using a pull up resistor. In this case, we are using a 100 kilo ohm R2 as the pull-up resistor. So pin 2 is going to read high volts, something less than 5 volts. So I can assume it's going to be close to 5 volts. So as you can see, we are either giving the pin 2 a 0 volts or 5 volts, depending on whether there is a switch pressed or not pressed. However, the goal is not to discharge the capacitor very quickly. So by making the time constant, so these two components control the time constant or the decay constant. And the goal is to choose a big enough capacitor and a big enough R1 such that the capacitor does not discharge instantly. So by holding that charge for a controlled amount of time, typically it is going to be related to the bounce times, average bounce times for certain switches, maybe 30, 40 milliseconds, maybe 60 milliseconds. Our goal is going to be to keep it on in one state for 100 milliseconds, but we can control how long we want that by adjusting the values of R1 and C1. So the goal is not to discharge C1 quickly. We are going to choose very high values for R1 and C1 to slow down that discharge. Let's see, pin 6 and 7 are connected together. That's another difference between the monostable and astable mode. Pin 6, as you guys know, that's the input to the threshold comparator, and pin 7 is the discharge pin. Let's see. So there's no second resistor here. We are only having R1. We have a switch that controls when the capacitor is allowed to charge. But the discharge only happens because of the values of R1 and C1. And we have another pull-up resistor over here to high, so that the bouncy switch can be in one of these two states, close and open, indicated by pin 2 being 0 or 5 volts, and our clean output or debounced output should appear in pin 3. Those are the differences, only differences between the previous and this one. um, Hold on. You are right, it seems frozen. I'm going to try to do this again. Okay. Uh, Bear with me, guys. There's some technical difficulties that are going on. Uh, okay, so I'm going to have to use a different approach. All right, so I'm going to have to do it a slightly different way. Are you guys able to hear, look at the screen okay now? Okay, so I recommend that you make the dock cam, is it moving? So let's do this. So now are you able to see only the screen with the 555 timer based debouncer? Okay, guys, help me out just a bit. Are you able to see my iPad screen um, and are able to see me write on it? We can see your iPad. Yes. Okay. And you are able to, of course, hear me as well. And you writing. Good. Okay. So we are uh, back. Okay. So let's quickly recap here. Pin 3, your clean output. That's what is desired. Switch 1 over here. That's connected to pin 2. That is what is the bouncy switch. So that's what we want to fix. That's the problem. And we are using a very high value of R1 and C1 to make sure that the capacitor C1 does not discharge quickly. It waits for a few milliseconds, few tenths of milliseconds to discharge, so that even though there is mechanical bounce, we are going to prevent that from not allowing the capacitor to discharge quickly. So that's how we are doing this. So let's talk about the design equations that go into this, which is going to be essentially the most important aspect of project 3, the design equations. And it is a very simple design equation, which is tau is equal to 1.1 times RC. And in our case, we had R1 and C1 because those are your two resistors that I'm going to highlight here. That's your R1 and that's your C1. So only those two are going to control how long does it take to discharge the capacitor, which means I'm measuring tau there. Let me use a different variable. Let's call it TD, T sub D, T discharge. So that's because tau is being used for um, time constant. I want to use TD for the time it takes to discharge that capacitor. So for example, that's the only equation that we need in project 3. So suppose we go and look at a typical switch, and the data sheet of that uh, push-pull switch or push button is suggesting that the typical bounce is about 100 milliseconds. If we find out that that value is 100 milliseconds, that our goal will be to discharge a little bit more than 100 milliseconds. So what we'll set is 1.1 R1 C1 should be greater than 100 milliseconds. And obviously I can have a value for R1, I can have a value for C1 such that this equation is satisfied. But note that I want to be very close to that 100 milliseconds, as close as I possibly can. I don't want to go to 99, definitely not, but I don't want to go to 150. Perhaps I want to be close to, my ideal is going to be 102 milliseconds, not too far away from 100, but on the positive side. Because I don't want to come back down before. I want to come back down a little bit later because I have a bigger problem of the bounce if I do it earlier. Let's go back here and talk about what do we do next. Well, I can take an approach like this. I can fix R1 to 100k ohm resistor based on what we have. So the way the screen looks on my end, I'm able to see the entire screen. But online, the student Haley says that she cannot see the entire iPad screen. Is that true for others? Okay, thank you. Let's see. R1 is 100K. So suppose I say, okay, I have a few resistors with me, and I'm going to choose 100K. And in fact, even the diagram says 100K here. So that's good. Then I can appropriately choose a value for C1 that satisfies that equation. So I'm going to go back and look at C1. So C1 should now be greater than 100 milliseconds divided by 1.1 times R1 times, sorry, just R1, which is 100K. So it is, and 100K. And if you can find that value out, which is going to be about 1 microfarad, is going to be very close to 1 microfarad, then that's your C1. So in this diagram, what we are going to do is we are going to use two values. C1 we are going to use 1 microfarad, and R1 we are going to use 100 kilo ohm resistor, and those are the design equations for the reason why those two values are appropriate. So if I go back here, now I know what this is. I know what this is. It's not a range anymore. It's 1 microfarad, and that is a pull-up resistor, so 100K resistor. That's, and this is the control pin, pin number 5. As before, we are not using that to control the voltage at P1. We are just fixing it to a constant, and C2 is going to ground with a very small capacitor there. So that's sort of a brief description of the project, some goals, some steps that go into building a hardware switch debouncer that is based on the 555 timer. Note that a switch debouncer can be built in other ways, in using other components as well. And online, if you search, you will find many different designs. This is based off of the 555. Let's see. Okay, so we talked about that. We talked about what happens. We talked about the design equations that go into this. Um, let's talk about what are we going to actually explore in project 3. So we talked about the fact that the switch goes from off to on state and back to off with a bounce in the middle. We talked about that. And what our goal is to clean it up such that the output is a clean low to high, high to low. So we want to remove the bounce in the switch. And to simulate this, the first goal is going to be to simulate this in PSpice. We are going to have uh, we are going to have to simulate a bouncy switch. Well, how do you simulate uh, too small? Simulate bouncy switch, because in PSpice capture, if you search, you are going to be able to find a switch, but it will not have bounce. So it will be a clean on-off switch. So how are we going to build a model of a bouncy switch? Well, we can model a bouncy switch by using several voltage sources. So you can see over here there are 5 voltage sources that have been connected back to back, and we have made sure that the voltages of the uh, voltage sources, the low and high voltages, are set in such a way, the time periods, the pulse widths, they are set in such a way that you get all those voltage sources combined, you get an output like this. So we have staggered those voltages, the low and high states, the period of those voltages in such a way that you get a combined effect of a voltage source that has a high state, then it has bounce for a little bit, then it goes to the low, then it has bounce again, then it comes back high. So we have used several voltages with changing different values to build a model of a bouncy switch in PSpice. So there are a few things that I want to warn you guys about this. A few problems that always occur when you simulate this in PSpice is the first thing. Well, there are many things that go wrong that I have noticed, but a few things that I commonly see happen are students, you know, um, do mistakes like this. They forget to put the millisecond where there is a M, they forget to put the M, so it doesn't look like this overall. Um, they don't connect the voltage sources in that particular polarity, that particular orientation. So as you notice, I'm going to highlight the positive side first. So V5 has a positive side on right side, right side, right side, up, up, and here. So all the blues are the positive side of those voltages, and then the negative side of the voltages. So while building this, you need to sort of keep track of the polarity of the voltage sources, and more importantly, it is going to be very sort of tedious to do this, but the numbers that you enter for each of these voltage sources is going to dictate whether you get a combined voltage effect of the bouncy switch or not. So make sure you double check, you triple check, you check several times what numbers you entered. So I hope I've given you some ideas about what are the common errors there. um, so if all of this is a fake switch, so let me just highlight this and say, okay, that is my fake switch or model of a bouncy switch. Model of bouncy switch. So if all of that is my bouncy switch, where does it go? So where does, where is that going? And of course, this is going to ground as shown. So that's fine. But where is that going? This says debouncer circuit, so I know that this is going to be the 555 based timer circuit, but which pin does that go to, that end go to? Well, for that, let me go back over here and look at where the bouncy switch needs to be connected. One more, and as you can see, the bouncy switch needs to be connected to pin number 2 on one side and ground on the other side. So I'm going to go back there and indicate that over here. So let's see, this should be not a question mark anymore, should be pin 2 or 555, and all the other circuitry that you saw, that goes in here. So R1 goes in here, C1 goes in here, uh, the 555 goes in here, all the wires that are connecting around that 555 go in there. Just the bouncy switch is shown by those voltage sources. What is going to be the output? Well, we know the output is going to be pin 3. That's pin 3, and that should be of course connected to ground using some load resistor. You can pick 1 kilo ohm resistor to do this experiment, to do this simulation. But your voltage probes, where are you measuring? Well, you're measuring pin 2 definitely. Why is that? Because you want to make sure that the pin 2 voltage looks like this, a bouncy switch. So that's definitely, you need to measure that. So that's going to be pin 2 voltage. So you need to put a voltage probe right over there to measure voltage. And you, of course, you need to do the same thing for the output. You need to put another voltage probe at pin 3, and hopefully if you do this right in simulation, and you pick the right values of R1 and C1 that go in the debouncer circuit, as you can see here, I don't know if you can see on your screen, but this value is 400 millisecond, that value is 500 millisecond. So we have, by choosing C1 to be 1 microfarad and by choosing R1 to be 100K, we have made the discharge time, what is that? Just greater than 100 millisecond, about 100 millisecond. So what should typically happen, what should happen here is, for all this time, because we are doing a simulation. In simulation, you don't have this. By the way, this is going to be important. In simulation, you don't have the pull-up resistor. Don't use the pull-up resistor in simulation. And if you read through the project 3 write-up, you will find that out. But R2, the pull-up resistor, not present in simulation, not in PSpice. So you will have all the circuitry except for the R2 being connected to high when you do that simulation. These details are of course uh, present in the experiment write-up, but that's what you need to do. So what happens is, when you if you do this right in your simulation, you should get an output which looks like this. You should have low until that place, should go high here, and then it should stay high for some time, and then it should come back down after that thing has finished bouncing and then go down. So that's what you need to observe if that is happening or not on pin 3. And as I said, these numbers that appear on the write-up, project 3 write-up, these are correct. You just need to make, because the number of voltage sources are 5 and each voltage source has about 7 parameters that you will need to adjust. It can very easily go wrong, so make sure that you check them several times if you don't get that correct the first time. Okay, so let's move on here. um, so that's your simulation, simulating a switch debouncer in Capture PSpice. So in the list of things that we are going to accomplish, PSpice simulation, we talked about that. Um, we are going to next move on to performing an experiment that uses fake switch data. What does that mean? Well, on the similar lines of using multiple voltage sources to sort of model a bouncy switch, I can use the wave gen functionality of the analog discovery to sort of make this voltage waveform, and then use that yellow wire to give that voltage to my debouncer circuit that I built on a protoboard. So instead of using an actual switch, the first thing that we'll do is we will use a fake switch, which is uh, essentially the wave gen. So that's fake switch data. That is step number 2. We'll do that today. And then we'll move on to doing an experiment with the real switch. And then the fourth thing that we'll do is take that real switch and trigger the 4-bit counter that we have built in experiment 7, and I have preserved that proto board. So I have that ready to go. So we'll do that. And then sort of the fifth uh, thing on this list is to improve average energy. So depending on how much time we have left and where we are in the discussion, um, we may or may not be able to do item number 5 today. If we don't get to item 5, then we can of course do this on Monday. So that's those are the things that will that are here, that are involved in project 3, and that's it. So it's a relatively short project, and it shouldn't take too much time. The PSpice is just one simulation, and I already talked about what are the things that could go wrong in the simulation. Okay, so I'll take questions for a bit. Actually, I'll stop the recording here and I'll take questions, and then we'll start with the building.